going to move, static friction is not appropriate, kinetic friction is. And so this is where if you plug in numbers from the very beginning, you might have an issue. But because I didn't, we can, so therefore, masses move. Therefore, use of K, not use of S. And take that, plug that in right there where we had our use of S. This is now 0.1, so that becomes 4.9. And we end up something should be above 2.45 and below 3.675.
3.0625.
And so we now have what the acceleration of the system is. Questions to hear? Because we're about to change something. All right. They've now cleaned off the surface, and they've put down some sort of sticky substance, and they've cranked up use of S to 0.7. First thing you do, check to see, is it going to move or not? So we're back to using use of S, pod in a 0.7 here, and we end up with
It will not move.
what do you get?
I have negative, I haven't done it all the way yet.
Negative 0.6,
Yeah.
125.
Negative 0.6125.
I just got out a negative number and knew it was.
Okay. Once you recognize it's negative, that means acceleration is in the negative direction, which doesn't make any physical sense. Mathematically, it's valid, but mathematically, or physically, what that means is that you have the system set up like this, and suddenly mass 3 starts moving up, and mass 5 starts moving off to the other side. If you could actually do that, we would probably end all pollution made by any motorized vehicle. Unfortunately, physics doesn't accept such a thing. The fact that it's negative. Therefore, what is the acceleration?
0.
Yes. Some people get the negative, they feel unhappy, they just stop, but the actual acceleration is 0 meters per second squared because object did not move. All right, questions? All right, let's do box on ramp. The full thing. Box on ramp is something that you will see again and again. So there's certain shortcuts after I sort of lay it out, certain shortcuts I'm going to just start taking on it. And if you have questions, just ask and I can go back and redo some of it.
Dr. Fox, I'm hanging out.
Yeah.
Do I get my cavity filled? Have fun?
Yes. How could he not have fun?
Rejoice.
Well-
Dentistry.
If you compare it to physics, of course it won't be fun. Nothing is.
Honestly, yeah. I'd rather be here than most of my classes.
mass, let's throw friction into it, use of S as point.
Yeah, we're going.
What? You too. See what it says.
This will still be on the recording, right?
Oh, I hope so.
Okay.
I'm assuming somebody might tell me if it stops.
I think you're still going.
Okay. All right. Now, what I find, one of the things I find interesting about use of S and use of K is I've done various experiments with this with students for years. Use of K usually comes out larger than use of S. I think more than half the time. Which to me says, at some point, it will be acknowledged, and I'll have a whole slew of students get Nobel Prizes. Anyway, until we get there, let's go through the steps. All I really care about are the forces acting on the box. So let's talk about the forces acting on the box.
Force of gravity.
All right.
Friction. The normal force.
Going which way?
Perpendicular to the surface.
All right. Those are the three forces. In which direction, so that's force diagram. In which direction is it going to accelerate?
Towards the ground.
Be more specific. Towards the ground?
Like diagonal to the ground?
Yeah.
Okay.
Down the, I would accept down the ramp.
Okay.
So we have acceleration going in that direction. Set up a coordinate system. Well, one of them, if you want to make the math easier, should be in the direction of acceleration. I'll call that I hat. The other one perpendicular to it. It doesn't matter if it's away from the ramp or towards the ramp. I'm just going to go away from the ramp. That is a right angle. Questions to hear before we get to the trick part?
Do we need any kind of special notation to show that we have a slanted I hat and J hat?
Just write it up. I just write it like that.
Okay. I think that would be acceptable on test.
Yeah.
Okay. We don't need.
I'm assuming you're not taking I hat to be, 1 degree off of the ramp.
Okay.
Decomposition. I got three forces here. Are there any of them that are not parallel or anti-parallel or perpendicular to my coordinate system?
Yes.
What?
The weight.
Yeah. Therefore, we need to break weight up. Normal force is parallel to J hat. Friction is anti-parallel to I hat. Weight is in some combination, so we need to break weight up. There's the, hey, I don't mind trig, let's do it that way. And then there's the, my mind's not working on trig right now, I need to do it some other way. So what I'm gonna do is the trig way first, and then I'll do the other way second. So I'm gonna draw, now every time I draw an angle, it kind of looks like 45 degrees or so. Doesn't really matter in the trig method. So I've got my ramp there. I'm gonna draw my weight. Weight is a vector that's acting straight down. The components I'm breaking it up into are gonna be, they need to be parallel or anti-parallel to my axes here. So I'm gonna break weight up into a component going down the ramp in the I hat direction, and then in the negative J hat direction. So this is gonna go down the ramp that way and that way. That should be perpendicular to each other. I know this angle in this corner right here, that's the 37 degrees. I'm just gonna label it as theta for right now. So, if this is theta, and that's a right angle there, because again, weight is straight down. What is this angle right here? Okay, or in general, the complement. I'm gonna label this as theta prime, just prime, theta plus theta prime is equal to 90 degrees. Now looking at the smaller triangle here, what does that make this angle?
Oh, 37.
Just theta. So I'm breaking weight up. If I look at that particular triangle there, I know this angle here is theta, that's a right angle. My hypotenuse is what I'm breaking up, which in this case is weight. This is my opposite side, this is W sine theta. My adjacent side, W cosine theta. Since these are vectors here, I got my weight acting down this way, and I'm saying that it is the sum of these two vectors, that if I take that plus that, taking direction into account, I'm gonna get weight in that direction. So my force diagram changes. I still have friction acting this way, I have normal force acting this way. Down the slope, I've got W sine theta. Into the slope, I have W cosine theta. I am saying that these are the same thing. This is just broken up so that all my forces are now parallel or perpendicular. And I understand that you need to go at some point.
Oh, I actually don't have that going on today.
Oh, okay. You told them to go figure it out for themselves?
Something like that.
Okay. Now that I have all my, I've broken up the only vector I have to, we're to the equations of motion. Okay, F equals ma, that's my template. I'm gonna have an I hat equation and a J hat equation. So we wanna go for it? It's okay if you're wrong.
But when I had the sine, W sine theta minus the friction. That would be it.
We're looking for an equation, we don't have an equation yet. This is an expression.
Equals the mass times the acceleration.
All right, there we go. Yeah. In the past, I've had, you know, one is too many, but I've had too many students just leave this part off, which is rather critical. All right, the J hat equation.
The normal force minus W cosine theta equals ma.
Not quite. Unless I misheard. You said equals ma?
Yeah.
What is acceleration in that direction?
I guess 0.
Yeah. M times 0. Now, eventually we'll get to the point where we'll just write equals 0 instead of mass times 0. But again, the whole purpose of picking our coordinate system that way is so that one of these equations is equal to 0. Then we have our equations of motion. Next step. Questions on these before we get to the substitution? All right, substitution. For what do we have an independent equation? Just go down the list. Do we have an equation for weight?
Yes.
Which is? You said yes?
Yes.
Okay, what is it?
sine theta?
No,
NG.
mg. So I got mg. Do we have an independent equation for theta?
Yes.
What is it? When I say independent, I'm talking about an equation that's going to be true whether it's this problem or any other problem.
No.
Yeah. Now, we do have a specific value for theta, so I didn't know if you're going to make the argument that theta equals 37 degrees as an equation. It is an equation, but that's not what I'm looking for here. So we have mg sine theta. Friction, do we have an independent equation for friction?